Okay, so in this video, I wanted to show you how you can compute the average power in an AC circuit. Okay, so one of the things, one of the reasons that we want to study the average power that is supplied to a load is that, we prefer to compute that instead of the instantaneous power because instantaneous power changes with time. Okay. For example, you can plot the power of an AC circuit, and since here we have a sinusoidal behavior, well, we can expect that the power could also have a sinusoidal behavior, and that power will be changing over time. And that complicates analyzing a circuit because the value is always changing. So instead of computing the instantaneous power to analyze how the energy is consumed in through all the elements of a circuit, instead of doing that, we want to compute the average power. And the average power essentially can be understood as the DC component of the power that is supplied. Okay? And the reason of computing the average power over a period of time is that we can, well, the average or this DC component, okay, does not changes over time. It's basically the same. Okay, this value does not changes compared to the instantaneous power that has this oscillatory behavior. Okay, and one way to compute the average power of an AC circuit, okay, the average power, okay, is equal to 1 over 2 times the amplitude of the voltage times the amplitude of the current and times the cosine of the phase difference between the voltage minus the current. Okay? So this is the formula that you can use in order to compute this component. Okay? So that is the main reason, no, that in which we are interested to compute this average power because based on this relationship, we can know how the energy is consumed. Okay? And since the average power does not changes with time, it's basically the same. Well, we can use this value all the time, okay, because it is invariant to time. Okay, another interesting thing is that the only elements that consume an average power is the resistive elements. Okay, for example, this resistor will have an average power, but if we try to compute the average power of a capacitor, for example, like the capacitor that we have right here, well, the average power of this element will be zero. Okay, so that is another thing to consider. And so in this problem, we want to compute what is the average power of this 4-ohm resistor. Okay, so again, based on this relationship, well, we need to know the value of the voltage and the current, and also the phase difference between the voltage and the current that is supplied to each of the elements of the circuit in order to compute this average power. Also, we want to compute the average power of the source, okay? And the average power of the source, okay? So how can we compute that? Well, we can use that relationship, but also we need the current and the voltage. So since we have here a circuit that is in series, well, we can compute the current of the circuit as follows. First, I will use a different color and I will apply the Kirchhoff voltage law to this loop. So since the current is flowing in this direction, we can say that we have here -5 with an angle of 30 degrees volts plus I times 4 ohms, that is the voltage drop in this element, plus I times the impedance of the capacitor, that is minus J 2 ohms. Okay? And this is equal to 0. Okay? And well, if we solve for the current, okay, you will notice that the current is equal to 1.118034 with an angle of 56.2 5650 degrees amperes. Okay. And well, this is the current that is flowing through the circuit. So at the end, we have the information that we need in order to compute the power. For example, in order to compute the power of the voltage source, we can express it as follows. The average power is equal, and here we need to be very careful on how we define the sign of the power source. You can observe here that the current is flowing from the positive to from the negative to the positive terminal. Okay, this current I. So we can say that based on the passive sign passive sign convention, we can say that there is a negative average power because the current is entering through the negative terminal. Okay. That means, or this negative sign basically implies that this voltage source is supplying power to all of the elements of the circuit. Okay, so we are denoting that with this negative sign, and we can compute the average power as follows. For example, we know the current that flows through the voltage source, and also we know the voltage of the voltage source. And based on this formula, we know that this average power should be equal to 1 over 2 times the amplitude of the source of the voltage source times the current that flows through the voltage source times the cosine um, between the cosine of the phase difference between the voltage source minus the phase angle of the current that flows through the source through the voltage source. So we can say that this is equal to 1 over 2. The amplitude of the voltage source is 5. And we also have here the amplitude of the current, that is 1.118034 times the cosine of, well, we have here the phase angle of the voltage of the voltage source, that is 30 degrees minus 56.56 5 degrees, and well, these are watts. Okay, so you plug in these values in your calculator, and you will notice that the average power, okay, of the voltage source is equal to minus 2.5 watts. Okay, and what else we can do? Well, now we can compute the average power of the 4 ohm resistor. So the average power of the 4 ohm resistor is equal to 1 over 2 times the amplitude of the voltage that is applied to this 4 ohm resistor. Okay, the amplitude of the 4 ohm the amplitude of the voltage of the 4 ohm resistor times the current of the 4 ohm resistor times the cosine of the phase phase angle of the voltage of the 4 ohm resistor minus the phase angle of the current that flows through the 4 ohm resistor. So here we need to compute this voltage of the 4 ohm resistor that is equal to the current that we computed previously times the value of the resistor, that is 4 ohms. And this is equal to, just 1 second, this should be equal to 4.47 2136 with an angle of 56.565 degrees amperes. Okay, so now we can use this formula, that is 1 over 2. We know the amplitude of the 4 ohm of the voltage of the 4 ohm resistor, that is 4.4721 times the amplitude of the current, that is 1.1180, okay? Remember that the current that flows through this circuit is the same for the three elements. And we need to compute the cosine of the phase difference between the phase of the voltage minus the phase of the current. So this is the phase of the voltage, that is 56.56 degrees, minus the phase of the current, that is also 56.56 degrees. And, well, we can say that the average power of the 4 ohm resistor, well, I was forgetting to mention this, no? Remember that here we are assuming that the 4 ohm resistor is consuming power. So we will place a positive sign in this section, okay, in order to denote that the average power is being consumed by the 4 ohm resistor. So if you compute this result, you will notice that the average power of the 4 ohm resistor is equal to 2.5 watts. Okay, so this is the average power of the 4 ohm resistor. And I want to show you what is happening to the average power of the capacitor. Okay, let's say the average power of the capacitor. So again, we need to compute 1 over 2 times the amplitude of the voltage of the capacitor times the current that flows through the capacitor. Yeah, I am referring here to the amplitudes, times the cosine of the phase difference between the voltage of the capacitor minus the voltage of the current of the capacitor. And, well, we are here missing the voltage of the capacitor, that is equal to the current that we computed times the impedance of that capacitor, that is minus J2 ohms. And this is equal to, just 1 second, I need to compute this value by hand. So 1.118034, and with an angle of 56.565 degrees, and times minus J 2 ohms, that is equal to, if we express the result in polar form, that is equal to 2.2368 with an angle of minus 50 degrees volts. Okay? And what else? What else? Well, with this information, we can compute the average power, that is 1 over 2 times the amplitude of the voltage of the capacitor, that is 2.2360, times the current in the capacitor, that is the same current that we have computed previously, that is 1.1180, and times the cosine, okay, of, well, we need to compute the phase difference between the value of this, well, the phase of the voltage of the capacitor, that is minus 50, minus the value of the current, okay? So I think that I committed an error here. I need to verify something that it seems a little bit strange for me. I think that I computed an error in this section. Let me correct that. Let me erase this. And also I will erase this just for a moment because I need to verify this voltage of the capacitor. So this is equal to, okay. Okay. So the voltage, no, there was an error here, was 2.2368 with an angle of minus 33.435. Okay, so now I can plug in this amplitude, that is 2.2368 2360. Remember that this is the amplitude of the voltage of the capacitor times the amplitude of the current that passes through that capacitor, that is 1.1180, times the cosine of the phase difference between the voltage of the phase angle of the voltage of the capacitor, that is minus 33.43, minus the phase angle of the current, that is 56.565 degrees, and this is watts. Okay, so the interesting part is that you can notice that the phase difference between of this argument of the cosine function is equal to just one moment, um, minus 33.43 degrees. Okay, these are degrees, minus 56.565 degrees, and this is equal to just one second, this is equal to approximately it is equal to minus 90 degrees. But if you compute the cosine of minus 90 degrees, you will have a zero. So you will notice that the average power, no, of the voltage of the capacitor, of the average power that is consumed by the capacitor is 0 watts. Okay. Okay, so that is interesting because based on that, we can demonstrate that the average power that is consumed by a capacitor or by an inductor is 0 watts. Okay, so you don't need to compute that power all the times. Okay, so this was a very basic introduction into what is the computation of the average power in an AC circuit. I hope you like it, and later I will upload a different video in which I will explain um, how can you, well, compute the average power of more complex circuits. Okay, so see you later.